Good. So in today's class, we're going to start on chapter 11, which is on elimination and nucleophilic substitution reactions. And these are kind of two very broad classes of reactions that, when you put it all together, make a pretty wide sweeping, very general scheme, if you will. And that's what we're going to be working toward. And I think we're having no fewer than 4 classes to cover chapter 11. Let me just double check that. Yep. So we'll try to end chapter 11 on Monday the 9th, a week from today. And trust me, we will use all that time. But to me, it has always seemed like, and you can feel free to disagree with me after you've been exposed to the material, but to me, it's always seemed like these SN1, SN2, E1, E2 reactions, learning them is not quite the same thing as, say, learning hydroboration oxidation, which is focused on a very particular functional group and a very particular outcome to a reaction. Instead, all of these are broad classes of reactions that can have any of a very large number of possible reagents, both organic and inorganic, that could be involved. So that's what I would say about that. And it all starts, all of these reactions that we're going to learn, I'll just tell you, today we're going to focus on the SN2 reaction. And I'll write down in a little while that stands for substitution, nucleophilic, bimolecular. But all of these reactions have one thing in common, in that they involve a bond between an sp3 hybridized carbon, so this guy is to be sp3, and the so-called leaving group. So maybe I'll get my colors on again. So I'm just calling it generically X for now. But the leaving group will often be a halogen. Not always. In fact, in just a short while, I'll show you another thing that we can have there for the leaving group. And as you might imagine, the larger the halogen gets, the better the leaving group, because the larger the halogen gets, the weaker is the bond to the carbon. And so we do require for all of these that carbon needs to be sp3 hybridized, or you're not going to quite have the right setup to do any of these reactions. So the whole thing, all that together, we generally call the substrate. And speaking as I am to a group of, I think, largely biology majors or something close to that, not all of you certainly, but I would be surprised if it wasn't at least 3/4 of you, you're well familiar with that term substrate. And we use it in exactly the same type of way that you would in biology. You would talk about the substrate of an enzyme, meaning the molecule that the enzyme acts on. Same thing here. The substrate of the reaction is the molecule that gets primarily acted upon. And once we put all that together, one thing we also notice is, regardless of what this leaving group is, whether it's a halogen or one of these other groups that we're about to talk about, in any case, this bond is going to be pretty heavily polarized away from the carbon and towards the halogen. So that's going to mean our carbon's going to have a partial plus charge. In fact, if you like, instead of the polarity arrow, you could just put delta plus at carbon and delta minus at the halogen. That's fine. It means the same thing. It communicates the same idea. So I don't care which method you use to show that. They're just two different ways of communicating the same idea. So all of these reactions are going to have that in common. And what that means for us is that the leaving group is eventually going to, well, leave one way or another. And so that means our carbon's going to have a partial plus charge on it. Or actually, in some cases, it will have a full plus charge and be a carbocation. More on that on Wednesday, I would say. But certainly any substrate that we could come up with, that's going to be true. As long as the carbon's sp3 hybridized, we're going to learn reactions for primary, secondary, and tertiary substrates. But we're going to focus on the SN2 reaction today. I would also say, and by the way, this is going to be true whether you're looking at a nucleophilic substitution reaction or an elimination reaction. All of these are going to involve species that look somewhat like this, though we'll need to get a little more specific when it comes to elimination reactions. Be that as it may, I also want to point out that in living, in biological systems, in the cell, I think you will generally, maybe not always, but generally find that the leaving group is going to be not a halogen, but a phosphate group of some kind. So phosphates are biological leaving groups. And I think you'll find that when you look at the biochemical pathways. We'll talk a little bit about metabolism next term. There's a chapter on metabolism. I think it's chapter 29. And so we'll go through it pretty fast, and we're going to leave out most of the biological function type of considerations. But I think again, I'm no biologist, but if I'm remembering right, we'll find a number of cases of both nucleophilic substitution reactions and elimination reactions. And in those, we'll find the leaving group is some flavor of phosphate. Good, so much for that. And in a typical nucleophilic substitution reaction, wait, let me see if I figured out how to do this finally. No. I'm just trying to move it down a little. No. Last try. Oh. Okay. There we go. Because I want to write up here nucleophilic substitution. So this is going to be our SN2 and SN1 reactions, fall under the category of nucleophilic substitution. And in a typical nucleophilic substitution reaction, we will treat our substrate with some nucleophile, some Lewis base. I'm just going to generically call it NU with a lone pair there. And in the product, regardless of whether it's SN1 or SN2, you will get the substitution product. And there will, of course, be inorganic side products. There might also be metal ions, other things that really we're not concerned with. But the major organic product will be the product of a substitution reaction. And I hope and think that you'll recall that in general, a substitution involves two groups switching places. And in general, for us in organic chemistry, we'll find they're double displacement reactions. They're of the type AX plus BY yields AY plus BX. And that's certainly the case here. So it's a typical substitution reaction that takes place with a double displacement. And that's in general going to be the case with the reactions we look at. This will hold true for both SN1 and SN2 reactions. Good. I just want to make sure I'm not forgetting anything. Nope, I think that's fine. What about elimination reactions? We'll get to those later in the week. We'll probably start on, certainly by Monday, maybe a few things on Friday. But we'll just to be a little more specific, but elimination reactions in general are going to involve a similar type of setup with the leaving group, except that we will need at least one hydrogen on one of the carbons next door. And then we're going to treat that with some base. I'm just going to generically use B for base with a lone pair. So some Bronsted-Lowry base of sufficient strength. And then our major product will be an alkene. And there will be other things as well. You'll probably have the conjugate acid of the base and maybe some other doodads as well. But the major organic product will be an alkene. And so this, I think you'll agree, falls into how we defined elimination reactions. Elimination reactions in general, they're also called decomposition reactions, mean that one thing falls apart into two or more smaller things. AB goes to A plus B. And I think you'll see that's exactly what we've done here. We've removed, I guess you'll also have the halide ion, right? So there's other inorganic species that are in there. But the major organic product will just be this piece. It'll just be the alkene. And that's going to be the one we're going to be mainly concerned with. But I think you'll agree this absolutely falls into the definition of an elimination reaction. Yes? I'm sorry? B stands for base, yes. Yep. And that's actually going to be a major issue. How can you know whether what you're looking at is a base or a nucleophile and how good it is at doing that? That's going to be something we'll probably largely get to on Wednesday. But it's an important question. Good. So I think that's really all I need to say by way of introduction. We're going to start with the SN2 reaction. And I'll write this down in just a second, but SN2 stands for Substitution Nucleophilic Bimolecular. And let me just give one brief warning here at the beginning, since it's something I remember even all these years later that when I sat when you were sitting was a little confusing. The 2 and the 1 in SN2 and SN1, likewise in E2 and E1, does not talk about the number of steps in the reaction mechanism. So it's actually going to turn out that the SN2 reaction is 1 step, the SN1 reaction is 2 steps, at least looked at in one way. So it's not talking about that. It's talking about the molecularity of the reaction, which I'm going to review very briefly, but you would have covered that in Gen Chem 2. So I think that's all I really need to say about that. Actually, before we get into the SN2 reaction in earnest, I do want to point out that there are other possibilities for this leaving group. And one of the most common other possibilities is these so-called sulfonates. We run into them a lot. So basically what you need to know is that the bond between carbon and halogen is roughly similar to the bond between carbon and oxygen, when on the other side of the oxygen, you've got a sulfonate ester. And one of the more common sulfonate esters used is this one. We call that a p-toluene sulfonate. P for para, which, let me see if I can manage to do that a second time. Probably not, huh? Not too bad. Which is usually shortened to tosylate. And likewise, this whole group can be abbreviated as ROTS or ROTOS. Your book tends to use TOS and OWL also. I'm kind of a TS guy, but I don't really care which you use. They're both perfectly acceptable. And incidentally, this does not have to be exactly that p-toluene group. You can take the methyl off and just have a benzene sulfonate. Perfectly fine, it'll still work. It doesn't even need to be an aromatic ring at all. You can just have S bonded to CH3. We call that a methane sulfonate or mesylate. And this begins to get real crazy. There's a whole bunch of other aromatic ones. These were all used in a whole bunch of landmark kinetic studies back in, I would say, mostly the middle part of the 20th century. There was a benzene ring that had a nitro group on it, and they called it a nosylate, not making this up. There was one with a bromine on it, and they called it a brosylate. I had nothing to do with this. This was before my time. I told you already about mesylate. You can also, instead of CH3 here, have CF3, or trifluoromethane sulfonate. And you guessed it, we call that triflate, which is really cute. But they all have these cute names, and they're all pretty much the same idea. You can just vary the group that's on the other side of the sulfur. But they all are alternate leaving groups to halogens. So please be sure that you recognize them when you see them and you understand what's going on. How do you make a tosylate or one of these other sulfonate esters? Well, they're very easy to make, actually. You start with an alcohol, and you would treat it with nothing other than the corresponding sulfonyl chloride. What am I doing wrong? Nothing. So if you wanted to make a tosylate, you use p-toluene sulfonyl chloride. You do need to add some base as well, generally a mild amine base. something like pyridine. You could also use triethylamine, which is just a nitrogen with 3 ethyl groups on it. That's also fine. Any amine base is good. And in the end, you will wind up with your tosylate in generally very high yield. And there are, of course, inorganic pieces as well. You would get the chloride ion and the conjugate acid of whatever your base was, either the pyridinium ion or triethylammonium. So you would get that also. But that's a salt, essentially, pyridinium chloride or triethylammonium chloride. That's going to be water soluble and will wind up in your aqueous layer and thus in the waste jug. Your major organic product will be the tosylate ester that you see, the tosylate type sulfonate ester. Or if instead of a tol group, you would a methyl group, if you used mesyl chloride, then you'd get a mesylate. Same thing. I would say that you're not responsible for the mechanism yet, at least not quite yet, except ironically, this mechanism is pretty much an SN2 mechanism. So we're pretty much about to learn the mechanism that you would get in order to make this type of compound. So I just wanted to put these sulfonate esters on your radar screen. That's basically my main point with what we're discussing here. Just being aware that they can stand in for iodide or bromide or chloride. They're another leaving group, and if anything, they're actually better than halogens in terms of leaving groups. And that's another thing we'll get to eventually. How do you know whether leaving group A is better than leaving group B, whether nucleophile A is better than nucleophile B? It's quite a big topic, but I will at least get you guys set up with the basics on that. We'll probably start talking about things like that next time. Certainly once we're done with the SN2 reaction, which I think we'll only get through partway today. I'm hoping to get through at least some of the characteristics of the SN2 reaction and go through a couple of examples. And that's really what we're going to focus on in this chapter. As we go through the SN2 and then the SN1 reaction, we're going to learn what are the characteristics of these reactions. How do we know we're looking at one versus the other? How do we know which is going to happen? If you want to skip to the end and see where we're actually going with all this, which is fine, you can certainly do that. What we're going to wind up getting at the end is kind of a grand scheme that you can use to figure out which type of reaction you're going to get. Am I going to get an elimination or a nucleophilic substitution? If I get a nucleophilic substitution, is it more likely to be SN2 or SN1? If an elimination reaction, are we going to have E2, E1, or this third thing called an E1CB reaction? And all that will be laid out for you. I have like a flow chart at the end of the class notes. And I'll just let you know even right now, as I often say about a lot of things, that flow chart is by no means the only correct way of summarizing this chapter's material. There are a variety of other equally valid ways to organize the information. But if in case you're curious, if you want to look ahead at what we're aiming towards, that's what we're aiming towards. We're going to start with the SN2 reaction, and we'll probably start out pretty slowly. It's undoubtedly going to take us into the next class to finish our discussion of the SN2 reaction. Once we've done that, we can go a little more quickly through the SN1 reaction because we can understand it by comparison to the SN2 reaction. And then once we have SN2 and SN1 down, as you might guess, E2 and E1 are going to be very similar in a lot of ways. And then we've got that extra one, the special one, the E1CB reaction, which a lot of textbooks leave out, but kudos to your textbook authors for leaving it in. And yeah, you might think, oh crap, it's another thing I'm going to have to know. Well, yes, but I can tell you from experience, and I'll answer the question in chat in just a second. I can tell you from experience that it leaves a really gaping and obvious hole if we don't mention that. But yes, my point back here was that this bond between carbon and halogen and this bond between the carbon and the halogen, tosylate or whatever other sulfonate group, those have a similar reactivity. So please be sure you get that down. That they both are leaving groups, and so these sulfonates can take the place of a halogen. But I've circled the bond that you need to look at. It's the carbon-halogen bond versus that carbon-oxygen bond. Those are relatively the same or relatively similar. And this again is how you make a typical sulfonate ester. Good. Other questions before we get into the SN2 reaction? Very good. Well, let's do that then. The SN2 reaction. Which again stands for substitution, nucleophilic, bimolecular. And every one of those terms is important. Again, I think you're already familiar with the terms substitution and nucleophilic or nucleophile. That term bimolecular would have been something that you covered in Gen Chem, probably Gen Chem 2. But in order to introduce this idea, I'll just give you guys a typical SN2 reaction. This is just one example of zillions of possible SN2 reactions. In a typical SN2 reaction, we're going to start with a nucleophile and our substrate. So our nucleophile will be, just as we said the last time, there's going to be a nucleophile, and what we said a few moments ago. So we're just going to stipulate that our nucleophile is the cyanide ion. You can also write that as Cn minus. But please be sure you know the structure of the cyanide ion and that the minus charge is actually on carbon. It's actually a kind of carbon ion. Interestingly, how did it take me 22, 25 years to notice this? Notice the minus charges on an sp hybridized carbon. I don't think that's a coincidence. And so our substrate, for us, we're going to say is methyl iodide. So there's our carbon iodine bond. I could just as easily have used bromomethane or methyl tosylate even. Any of those would also have worked. And we can expect that our product is going to be one in which the cyano group replaces the halogen. And then we will also get the iodide ion, plus probably some other things. And I should mention also that of course, you can't have a bottle of cyanide ions. There needs to be some countercharge. There needs to be a spectator ion. And most nucleophiles, I think you'll find for SN2 reactions anyway, are provided as the sodium or potassium salt, or maybe the lithium salt, but there'll be some alkali metal cation. So it might be that we're treating methyl iodide with sodium cyanide or potassium cyanide, but you'll most likely be given that as an alkali metal salt. And that will also, so if you used sodium cyanide, you'd wind up with sodium iodide at the end. If potassium cyanide, you'd get potassium iodide. None of which really matters. That's water soluble. That's going to wind up in the waste jug. We're mostly interested in the major organic product, and that it could be one of the 3 or 4 worst triple bonds that I've ever drawn. There, that's better. So we'll get acetonitrile as our product, happens to be what that guy is called. But we will get a new carbon-carbon bond in place of the carbon-halogen bond, and I think you'll agree with me that we've substituted the halogen, the leaving group, for our nucleophile, just like we said when we introduced nucleophilic substitution reactions maybe 15, 20 minutes ago. And the same type of thing would happen in an SN1 reaction, but in a very different kind of substrate and with a very different kind of mechanism. So one of the characteristics of the SN2 reaction is that for best results, we'll want to use a methyl or primary substrate. And I think you'll agree we have that here. That substrate is methyl. And so the SN2 reaction, for reasons which will slowly unfold, works best, is most effective with a methyl or primary substrate. Secondary is kind of your intermediate case. It might work a little bit. You would probably get a low to moderate yield, but it might be sort of okay. Tertiary substrates are right out. Those do not react with an SN2 reaction. They're going to turn out to react by an SN1 reaction, which we'll learn about next time, or at least we'll start to unpack that the next time. So that's one characteristic of SN2 reactions that you will need to know, that they work best for methyl and primary substrates. Another characteristic of the SN2 reaction that you'll have to know is that its mechanism is concerted. There's just one step. And in that mechanism, the nucleophile attacks the substrate. It attacks the carbon in the substrate that has the leaving group attached. And we break the bond between that carbon and the leaving group all at the same time. Those two things happen at the same time. We form the new bond between carbon and the nucleophile at the exact moment that we break the carbon leaving group bond. So that's another characteristic of the SN2 reaction. Its mechanism is concerted. There's just one step. And so that's why I said the SN2 reaction is one step. So again, the numbers in SN2 and SN1 and E2 and E1 do not correspond to the number of steps in the reaction mechanism. They correspond to the molecularity. So what do we mean by that? What do we mean by molecularity? What do we mean when we say that this reaction is bimolecular? Well, there's two different ways of saying that, which essentially each of them implies the other one. They're just two different ways of saying what we mean that this reaction is bimolecular. One way that we can state it, that we mean by it being a bimolecular reaction, one thing that we mean when we say that is that there are two molecules or two species involved in the rate determining step. Determining step. That's one thing that it means when we say that a reaction is bimolecular. Now, how do we know that there's two species involved in the rate determining step? Well, first of all, I think you'll agree this reaction has only one step. So by definition, that step must be rate determining. I can even write RDS for rate determining step. Another thing that you can write for rate determining step is slow, right? The rate determining step is always the slowest step, again, by definition. Any other steps will be fast compared to that. But here there is only one step. So it must be the rate determining step. And I think you'll agree there are two species involved in that mechanism. Both the nucleophile and the substrate are involved in that step. So that's how we know that this is a bimolecular reaction. There's two things involved in the rate determining step, two molecules, two species. That's one way of saying it. Another way of saying that the reaction is bimolecular is to say that the rate law is second order. It's not a different thing. They're just two different ways of saying the same thing. And indeed, for this particular reaction, the rate law would look like this. It would be rate is rate constant times, in this case, the concentration of methyl iodide times the concentration of the cyanide ion. And I think you'll agree that rate law is second order. Remember, to get the order of the reaction, you add the exponents of all concentration species. And so the exponent for both of them is 1, right? They're both raised to the first power. 1 plus 1 is 2. It's a second order reaction. So this is what it would be for this particular reaction. Or in general, the rate law for an SN2 reaction would be rate constant, or rate equals rate constant times substrate concentration times nucleophile concentration. Can I go NuCl for nucleophile? That's for any SN2 reaction. No exception. Every single SN2 reaction will have that rate law. And actually, the opposite is also implied. if you come across a reaction in the wild that has that rate law, it is definitely SN2. Absolutely for sure, no exceptions. So the implication goes both ways. Good, and I think that's all I really need to say about that. What I want to end with is the nature of the transition state, which I think also gives us some information on the reaction. And that is, first of all, the mechanism of an SN2 reaction. We're still learning characteristics of the SN2 reaction. So the mechanism goes through a planar transition state. Can I go TS for transition state? I'm sure I can. And not only that, another thing which I'll just mention here, we'll probably start here in Wednesday's class, is that in cases where the substrate is chiral, the mechanism goes by complete inversion of configuration. Goes through 100% inversion of configuration. And you'll only notice that if the carbon's chiral. If the substrate carbon that bears the leaving group is chiral. Inversion of configuration. So I'm going to showcase both those things by starting us off with a chiral substrate. And the one I'm going to specify is this one here. Here I'm putting D for deuterium. And so as a reminder, D is deuterium, which is hydrogen 2. So deuterium is a heavy, stable isotope of hydrogen. It's not radioactive. And so you get a deuterium nucleus by adding a neutron to a regular hydrogen 1 nucleus is just 1 proton. So a deuterium nucleus is a proton plus a neutron. So if you ever see D, that's what they mean. They mean deuterium. They mean hydrogen 2. And to this, let us say, sodium acetate. We'll use that as our nucleophile. And again, hopefully you recall the structure of the acetate ion. So there's our acetate ion. The sodium ion isn't involved, of course. That's just going to be the counter ion to this. But acetate's going to be our nucleophile, and the mechanism is going to be just what we said a moment ago. The nucleophile is going to attack the carbon bearing the leaving group. It's going to come in from behind the leaving group and break the bond between that carbon and the leaving group. Those two things happen at the same time. It's concerted. And when that happens, the thing you need to be aware of is when the nucleophile comes into the leaving group, or comes into the substrate, it pushes on that carbon atom, and these groups that are attached to that start to move. So again, the nucleophile, on attacking that carbon, pushes on it, and the other 3 groups start to move. And so if one were to draw the transition state, which normally we don't, but if we were going to do that, we would show a bond forming between that oxygen and the carbon, and the bond between the carbon and the leaving group breaking, and the transition state will be planar. So now there's going to be just a moment where that carbon that bears the other 3 groups, while the one bond is breaking and the other one is forming, that carbon is for a moment planar. And this is a transition state, so we'll show that with square brackets and a double dagger. Normally, we don't draw transition states, unless it specifically says to. But we're going to have a little bit of plus charge on that carbon and some minus charge on both the incoming nucleophile and the outgoing leaving group. And then I'll end with this. I'm actually pretty much out of time. In the end, that motion, if you will continue to happen. And let me move the chat box out of the way. So we will get a product that looks like this, in which the deuterium's over here, hydrogen over here, and if you work it out, You can double check me on this, but I think I'm right. That compound turns to be in the S configuration, and the starting material is in the S configuration. If you work it out, I think you'll find the product is in the R configuration. So if we start with 100% S, we get 100% R in the product. You only notice that when the starting material is chiral, but that is a property of the SN2 reaction. The mechanism always goes through 100% inversion of configuration. And I think that's a good place to stop, especially since I'm out of time. So, have a great day. I will see you all on Wednesday.